In Chem 1, we did a lot of talk about changing phases, going from a solid to a liquid, liquid to gas, gas to liquid, etc., etc. This chapter is going to zoom in a little bit more on that whole process. Now, obviously, if you're going to change from a solid to a liquid, liquid to a gas, you have to add heat, and there's going to be a change in temperature. Okay? This line right here is going to represent a solid, or a solid being warmed. This is a liquid being warmed, and this is a gas being warmed. Right here, this is called your enthalpy of fusion, otherwise known as melting. This would be your enthalpy of vaporization, otherwise known as boiling. And remember, the temperature at which all of this takes place depends on what kind of intermolecular force the substance has. Solids, for example, this is a representation of a solid that is polar, so this intermolecular force right here would represent a dipole-dipole attraction. The heat of fusion is the amount of heat that's necessary to stretch this intermolecular force. This is why the molar heat of fusion is always a positive value. You have to add heat in order to stretch that force. Melting is always an endothermic process. So the enthalpy of fusion is the amount of heat absorbed as 1 mole of solid liquefies. Liquids still have the same intermolecular force, but they're a little bit stretched out. Okay? These forces are still strong, but not as strong as they are in the solid. The heat of vaporization is the amount of energy that's needed to actually break that intermolecular force right there. So it's the heat absorbed when 1 mole of liquid becomes a gas. Energy is required to sever the intermolecular forces of attraction. Vaporization is always endothermic, just like fusion was as well. And remember, ideally, in a gas, they don't have any intermolecular forces. Vapor pressure, when molecules leave the surface of a liquid, when liquid starts to evaporate, it enters the gas phase, they exert some sort of pressure. Gases have pressure. The vapor pressure exerted depends on the rate of evaporation. The rate of evaporation depends on the temperature. So here I have liquid water. It is evaporating, yet some of it is also condensing. If you're in a closed system, you develop some sort of equilibrium. Water plus heat produces gaseous water. If I increase this heat, this reaction will shift this way and increase the amount of water vapor or gas. When the water vapor pushing up is equal to atmospheric pressure pushing down, that's called boiling. Evaporation occurs inside the liquid right here. Okay, so those little bubbles that you see in water that's boiling, that's not air. Those are actual water vapor bubbles pushing upwards. Notice that water boils at sea level at 100 degrees Celsius, but if we go up to Boulder where there's less air, so therefore the atmospheric pressure is lower, then water is going to boil at a lower temperature. If I keep going up and up and up, there's less air, less air, less air, less air pressure. Therefore, water will boil at a lower temperature, and if it's boiling at a lower temperature, it's going to take longer to cook that food. The vapor pressure on the surface of a liquid depends on the strength of its intermolecular forces. So if you've got London dispersion forces, it's not going to really take much. If you have hydrogen bonding, it's going to take more energy to increase the vapor pressure. Now, even though argon weighs more than methane, argon has a lower enthalpy of vaporization because methane is a little bit more spread out. Okay, but as we go down, these have dispersion forces, London dispersion forces, London dispersion forces. This one's a little bit more polarizable, so it has a higher vaporization point, higher boiling point. Water is polar. It has London dispersion forces. It also has dipole-dipole forces, but it also has hydrogen bonding, which is stronger. That's why it requires more energy for it to boil, even though it's smaller than benzene right here. Okay, it's less polarizable than benzene right here, but it is a polar molecule and it has stronger intermolecular forces. Therefore, it has a higher boiling point. Okay, we're going to start doing some phase diagrams, and when we're talking about a phase diagram, we're talking about a container like a piston right here where you can control the pressure and you can also control the temperature. So here we are. We're going to have pressure on the y and temperature on the x-axis, and we're going to go ahead and start with water. Water, if you'll notice this line right here, this is your vaporization line, okay, or your vapor pressure line. Gas and liquid coexist on the red line. So whenever you're on this red line right here, you are boiling. If you're above the red line, you're a liquid. If you're below the line, water will be a gas. Okay? One atmospheric pressure is called normal, right? Normal pressure. So this right here represents the normal boiling point of liquid water, which is 100 degrees Celsius. This line right here represents the line of fusion. Okay, on this line right here, a solid and liquid coexist in the cylinder when it's on that blue line right there. So that would be like the freezing point. This right here at 1 atm is called our normal freezing point, okay, which is 0 degrees Celsius. Anything on this side as far as pressure and temperature is concerned, so at a very low temperature, you're obviously going to be a solid. Anything right here is still going to be a liquid. Okay, so if I give you a certain pressure and a certain temperature, you should be able to tell me if it's going to be a solid or a liquid or a gas. Now, water is one of the only substances that has a negative slope. The slope of this line goes towards the left. And that is because water is one of the only things that when water freezes, it expands. And when it expands, its density goes down. So solid water floats in liquid water. Most solids are more dense than their liquid form, but water is the opposite. Ice floats in water. And it also means this: if I take some solid ice and I increase the pressure on it, it's going to turn into a liquid. If I take liquid water and I decrease the pressure, it's going to turn into a solid. This line right here represents the line of sublimation. That's going from a solid straight to a gas. So from here to here, that's called melting. From here to here, that's called freezing. From here to here, that's called boiling. From here to here, that's called condensation. From here to here, that's called sublimation. And from a gas to a solid, that's called deposition. This point right here is called the triple point. The triple point is the point at which all three phases coexist. So at a pressure of 0.006 atms and 0.01 degrees Celsius, all three phases of water can coexist. The triple point is an equilibrium between liquid, solid, and gas, liquid, solid, and gas. Basically what you have is a piece of solid sitting in a boiling liquid substance. This point right here is called the critical point. Beyond the critical point, you can't distinguish between a liquid or a gas. So the critical point is the temperature beyond which temperature and pressure beyond which the entire system becomes a supercritical fluid. What's a supercritical fluid? It's too dense to become a gas, yet it's not dense enough to be a liquid. You can't distinguish between the two. You can't tell if it's a gas, can't tell if it's a liquid. Alright, notice this is the phase diagram for carbon dioxide. Notice that its line of fusion right here has a positive slope. Almost everything has a positive slope except for water. So if you increase the pressure, it will solidify. Whereas with water, if you increase the pressure, it will liquefy. Okay? Notice that carbon dioxide's triple point is above, way up here at 5.1 pressure. In a room, like the room that you're in right now, which is around 1 atm, you can have solid carbon dioxide and you can have gaseous carbon dioxide at our temperature. If you have dry ice, that's solid carbon dioxide simply subliming into a gas. But you cannot see liquid carbon dioxide in a pressure of 1 atm. Describe the phase changes that occur if carbon dioxide is kept at negative 52 degrees Celsius while the pressure increases from 1 to 50. So here's negative 52 degrees right here. Here's 1 atmospheric pressure. So as I start to go up here in step 1, it's just a gas. Once I hit this line, however, then it's the boiling process, so I have liquid and gas. If I keep going, this is just a liquid. Once I hit the blue line, that's that liquid turning into a solid, which is called freezing. And then beyond that point, you just have a solid.